Oh, sorry about that. Forgot to turn on my mic just now. So 2 hours and 2.5 hours for the previous video, 1 hour for the first video. So in this way, I think people can just straight come to this video to look for the Lab1. Okay, I presume you can hear my voice now. Okay, let's change it to Thevenin theorem. All right, so for the introduction one, you still need to do it yourself. I only show you the example. Let me copy this one. Okay, let me copy. But it's better for you to rephrase all the sentences, you see, not to copy exactly the same. Let me read the rubric again, whether it allows you to do that or not. Let me see. Introduction complete and well written, but you didn't say well copy and paste, right? So this tells me that probably you need to rephrase the sentence. It says just copy and paste all the content. So logically you have to rephrase all the sentences here. You see, probably you can use the the figure here. I think you can use a figure here, so be okay. But with today's technology, I think it's not very hard for you to find another explanation, right, for this Thevenin theorem. You can just go to the Google and anytime I think you can find the some other speaker how they explain about this. Sorry, how they explain about this Thevenin theorem. I think more than 100 people should explain this one on the internet. I just simply pick one. Thevenin theorem stated that is the something right. All right. How come suddenly I have a hiccup? Okay. There are plenty of resources online, so I'm not going to worry too much about this. I think you think the same way too. Okay, but still in your report, you need to give a bit introduction because this is required by the rubric. Then I would straight away jump to the procedure. Step one. I skip the rest. I think you do it yourself. Okay. All right. This time will go much faster, right? As you can see, probably 1 hour we can get it done. Let's copy the first step. Always leave a space between and do a nice element. Okay, and don't forget about the formatting also. Bold and 14 for the main title. Okay, let's read about it. Construct the circuit shown in 2.3. Okay, that means we need 2.3. Let's copy 2.3 here. This time I'll just go ahead and copy the figure 2.3 also, including the title. Okay, it's okay. It's put into the next page already. Construct the circuit And okay, let's construct the circuit. So for this circuit, we have to save it. We can just save it for the future. Make sure you save it with a name that you can recognize later. So let's save it with something that meaningful. What is that? 20022nd B, circuit 81, question 1. Okay. Assignment 2, question 1. All right, then we can start with a new one. New schematic. Okay. Before we begin, just go ahead and save it first. Okay, use the previous name. Use the previous name. Change to question 2. Now, let's view the grid in the beginning. Let's view the grid. Now let's construct this circuit. 3 resistor. Okay. Take first one, rotate it, Control R. R1 is here. R2 vertical, R3 vertical. Rotate. And here, and here. And escape. Then we insert the voltage source. Remember, come here, come to components. Then the voltage. And the default one is the one we need. Okay, escape. And we right click and insert, enter 12 volt. It's okay to enter V here. It's easier for the reader, 12 volt. If you key in 12, sometimes the 12 can be the not number, right? So better to key in 12 volt here. And don't forget about the ground. We have 3 ground here. We don't want to modify the circuit in any way. We try to follow exactly the same. Place the ground at the button here, here, and here. Okay, exactly the same as this one. This to play safe. Then the last thing to do is, of course, the wiring. Connect the wires. With the grid line, of course, it's a bit easier, you can see. With the grid lines, things that looks a bit easier. Without the grid line, sometimes you are not so confident which point to connect to which point. Now I'm going to use a scroll to zoom in a bit to something I feel, to the size I feel comfortable, and then use a pen to centerize it. Okay. Of course, not to forget, key in the enter the value 1.2K. Right click 1.2K and 10K here. As you know, we can do a bit faster, right? For the second line onwards, 3.3K. Okay, I also try to be slow down a bit, so that every student can catch up. Okay. Oh, this is a previous one, right? So this link to what? Okay, let's continue. All right. After done the circuit construction, let's consider R3. Where's R3? So, okay, I have to make it clear to you guys now. R3 is not, even though it appears as a part of the circuit, actually the main part of the circuit is only R1 and R2. You can see here. R1 and R2 form the internal circuit we call the RTH, Thevenin resistance. Terminal A and B is connected to the external. This is considered the external. So what it means is, Jerry, in other words, you say that the load can be changing. You see, you can change the load to any other value, but this is an internal one. You cannot change it. In other words, also means RTH, these two, is already built in the device. It's something that the user cannot change, but the user can attach a different load, different lamp size, different resistance size to the output. This is output, right? A and B is output, but here you cannot see A and B here. Actually, A is here, B is here. The invisible A and B are here. The Thevenin circuit actually simplify the device. Let me give you some breakdown information, a quick one. Let me give you a quick one. Some introduction. Otherwise, it's hard for me to explain later on. You see. Let's say you are one day you design your own circuit, okay, with certain voltage and resistance and some other resistance, right? Let's say something like this. Okay, and then you assume that the user will attach external load to these two terminals, A and B. Okay, so this is your internal resistance R1, R2, R3. Then what would you do actually to make the job easier for the user? You will package everything here into a really simple equivalent circuit. We call it equivalent circuit. Equivalent circuit. We in this case we call it the Thevenin equivalent circuit. Okay, so Thevenin equivalent circuit looks like this. We convert the V into VTH. We convert all the R to RTH. So this, the original circuit now converted to something really simple with only V and R. So now we package this one. We show this one is another equivalent circuit of this device. Actually, both of them are the same. Of course, from the user point of view, this circuit will look much simpler than this one, right? Original circuit could have many resistance inside. This one only have one resistance. So if the user attach this A and B, so presume this is A, not B. So the user just attach this one to one external load. Usually we call it RL, the load. It's easier for the user to analyze the circuit, you see, because the total resistance here will be RTH plus RL. The total resistance is equal to RTH plus, because we only have two, right, in this circuit, but there are many here. So this is rather confusing. Here's rather simpler to work on. So the R total would be RTH plus RL, right? Looks very simple. We only have one voltage source. Therefore, the current flow to the RL, we call it IRL, would be V over I, V over R. So it would be the VTH over the RT. This is what I mean actually. I mean, for the user point of view, they can easily calculate the current flow to the RL by using the simple Ohm's law without going through all the circuit analysis. You can use a simple Ohm's law to calculate what will be the current, output current, what will the output current be, and also the power. The power sent to the RL or the power absorbed by the RL will be using the power equation like this. So the I will be IRL here. Current flowing through RL, IRL plus the RL, sorry, multiplied by the RL is a power. So for the user point of view, you make the users easier to calculate the current and eventually calculate the output absorbed, or I mean the total output for the load. What the maximum power can be absorbed by the load. That is the purpose of the Thevenin equivalent circuit. Another way you can say is kind of like simplify the circuit into much simpler equivalent circuit like this. So we have for the original circuit we have 3 resistors and 1 power source. Of course, we want to convert it to something like this. So we need to follow the procedure. So I think now you understand why this statement says that consider R3 to be a load. So remember, R3 always is external to the circuit. This is our actual circuit we want to convert. R3 is just a load only, represent a load like this. You clear about this? One more time. R3 is not the whole circuit. R3 is only represent the load here. So the RTH must be based on R1 and R2 only. You clear about this? RTH must be calculated based on these two only. Okay, exclude R3 because R3 is our load. Okay, you clear? Now we can proceed. Run the simulation, okay, using the same operating point analysis OP. I think we can do that, right? Okay, let's first come to simulate, edit, and then we choose the last one, operating point, and then click OK, and then press it below here, near the ground. Then we can click the run icon to simulate it, okay? So we get the result immediately. So whether this is correct or not, let me double confirm. Looks like it's correct. Okay? Looks like this one's quite familiar. All the number here is quite familiar to me. I think I've seen it somewhere, sometime. Okay, you know what to do, right? Is to copy it to your Word file. So I use the same old trick. I press the print screen. Then I come here. Then I save this one. So this one is 3 first. Then I start with a new one. And with all the image here, I'm interested only in this part. Only interested in this part. Then I cut into my worksheet. Remember, it must be under the result, right? Not under the procedure. You must place it under the result section, under the result title. And don't forget about the title also. The title for this figure. Okay, this going to be figure. Let me check. We have figure 2.3, 2.4, 2.5. So look, this one looks at figure 2.7. Okay, let's name this one as figure 2.7. Step 2 or 3? Step 1 only. Step 1. Step 1. Step 1. Yeah. You guys can follow or not, actually. Leave a space here between data. Leave a space here. Save it. Now, step 2. Oh, just I say that whether the result is correct or not, right? Looks like it's correct. See, looks like the result is correct. I didn't see it, any discrepancy actually. I see the result are quite tally, all the value are quite tally. I didn't see any error there. Okay, so let's continue. So far so good. No issue right now. So step 2, we want us to point at the node and to find the node voltages. You see, by pointing at a node to check the voltage or mass, to check the current in the LED space. Measuring the current through the R3, voltage through the R3, record them down here. But this time we record them down here, record them down under step 2, see? It's not I think this time it's better put them record them down here together with the step. If we put under the result, it will be very confusing, you see? I think do it this way. I think it's better to. We need to find out these two values. So I'm going to cut these two out, so I can type something in. Actually, if you are using this Microsoft Edge browser, you can straight away type this one in here and then copy and paste. You don't need to do that. You can save one more step. You can come here to type it in here and copy and paste it later. See, we don't need to copy out to this Microsoft Pen. You see, we can save one more step. Okay, and then let's do it this way. Make sure you open up the worksheet in the Microsoft Edge browser. All right, just follow the instruction by pointing at a node to check the voltages. Okay, how do you do this? Let me show you. Pointing at this node and click. Pointing at this node and click. This node and this node is the same, right? How about the currents? Let's point at this component and click and see what happens. No result, right? Looks like the current we cannot do it. I remember we can do it somehow. I remember. Oh yeah, by doing this. We need to do some configuration. So let's point the voltages here. Even though we know it's the same. You see they're crashing into each other, right? The result. So what can we do now? Can we remove this one? Use a scissor. Remove this one. Looks like we need to pull this one away from this node. Okay, let's try the move. The move is what? Wait. F7. Let's click this one and press F7 and move this one away from here. It's a mess now. Delete. F7, move this one here. Because later on, we want to show the current. That's why I'm moving all this component away. Okay, now is the time to show the current. Okay, but you cannot show the current directly, as you know. You only can show the voltage first. So I put here to show the voltage first. Okay, then how do I change the current? Right click. Here's a current R3, right? R3. So what I need to show is a current R3. I select this one. Double click. Current R3. So you appear $sign IR3. Click OK. Looks like I need to remove the $sign. Looks like I need to remove the $sign. Let's try OK. Now you can see that this is a current flowing through the R3. So this is a negative sign. Why we have the negative sign here, but we don't have the direction? We don't know it's from where to where. It's okay, you know. As I told you in the first tutorial, the sign is just indicate that going opposite of what you have assumed initially. It's going opposite direction. So not to worry about the negative sign right now. We just focus on the absolute number. That is the throw away the negative sign, throw away all the sign. Look at the absolute value. So there will be 2.45 milliampere. So IR3 here, change it 2.451 milliampere. Since there's no unit behind it, so we better type MA. Okay, how about the voltage across VR3? So this voltage here, and then the other voltage here is ground, 0 volt. If you don't believe me, you can click here. From this node to this node, in between is 8.008. So just type it in, 8.088 volt. Is it? Right, simple. Now use our tools here and import it to our reports. Here, place under the step 2. See, it looks very nice, right? Very nice. I think your boss will be very happy to see this really nice, nice report, properly prepared. All right. I don't know whether you can follow or not. Just now I go through one step to show the current. One more time, you just right click and then you click on I3. Make sure here the command is I3. Or you can just go ahead and type I3 also. But we have to be follow exactly the same IR3, you see. You cannot I bracket R3, sorry. Then the software will show you the current in this branch IR3. Of course, if you type in IR1, it will show the IR1 here. So do make sure you type in the correct name. This IR3, here's IR1. Okay. But to show IR1, you probably need to change this one, or you change this one to current. You have to change either one. But at this step, we only worry about R3. Okay, we are not worried about R1 yet. Okay, next step. Now what we're going to do? By using Thevenin theorem, we calculate the current through R3, the procedures also. So when come to the calculation part, you need to wait until you learn about this Thevenin theorem. All right. But for now, we just copy it. Okay, we just copy it first. For now, we just prepare it so that in the future we just need to calculate it. See, we have this noise here. We need to remove. Read again, read proof again. Now, by using the calculator R3, the procedure, you need to provide all the work in the space provided. So the space provided means in the result section. Okay, in the result section, you need to show how you get the how do you calculate the VTH. Okay, how do you calculate the VTH with your theoretical steps. Okay, so you do just that. Okay, after show all your work in detail. Hey, wait a minute, how come this one appear here? Wait. This one should appear at the top, right? Let's put it back. Okay. Now 3. Let me put the notes here. Okay, you need to show your calculation step in the result section. So what you do here is you come to the result section here. Oh, wait a minute. Is it better to do it in the discussion or result? Let me see here. Let me usually I think should be in discussion. Let me read about this again. Very complete data discussion and good understanding of the result. Number simulated result graph table are correctly presented. Results. Either way, I think it's okay. It didn't clearly tell us where to put the calculated value. Discussion is just to discuss something, right? Looks like it's better to put at the result section. So you say, first you need to refer to the step number. What is the step number here? Let me see. Very good. Yeah. Step 3. Actually, never mind. Let's just do it. So you do it here, okay? Show everything here. Okay, show everything here. All right. This is the notes. The one in the bracket means just a notes. Okay, now we can continue. Because as you know, you need to attend the tutorial 2 and 3 in order to come out the equation. Okay, let me. Do I need to give you an example? Let me see here. I think it's quite simple. So I don't think you need that. You need because the solution is quite simple. Okay, it's quite simple. PTH. How to find the PTH? I think it's better not for me to show it here because it's too simple. If I show it here, that means you don't need to do it. You don't need to think yourself. You just need to copy it. Let me skip this step for now. Let's come to step 4. So this is what? Figure 2.4. Figure 2.4. So let's place the figure 2.4 here. Oh, one more time. All right, 2.4 here. So you show your calculation in the result section. You can type something, say all the calculation would find the calculation in the result section. Result section. Find the calculation in the result section. Okay. Now step 4. So verify the VTH by simulation. So now instead of just a calculated the VTH, we want to use a simulation the tools, the software to help us to find the VTH. So let's learn how to use the tools to help us find out how to use a computer to find out the VTH. First, I will copy the step. Okay, then what? The recorder still on, right? Yeah, all right. Verify the actual VTH by simulation. So in order to verify it, we need to construct a circuit like this. We need to measure the voltage here. We need to measure the voltage here. You can see the R3 has been removed from the circuit. R3 has been removed from the circuit. So it's easy to do, right? So what we do is take the scissor and remove this R3. Then what? Then what? Then run the simulation again. And we have different voltage output now. Because there's why you see the question mark here, because remember the question mark is the IR3. Because there's no R3 now. That's why the software don't know how to continue from there. So it's for us to do is just cut this question mark away. So apparently this is the answer. And I can tell you this is the correct answer also. This is the correct answer. Okay. So what to do? This is your evidence, right? This is evidence of showing that you have done this step. That means you need to copy this screen. You need to copy this screen and put under the with the dot is okay, you know, with the all the grid is okay. Or not. Let's place it here, okay? Resize it a bit. Remember to put the title so that people know what to do. People know what it is. Let's see, 2.8. This is a simulation result. For step 4, finding VTH. $10.714, 3 decimal points. I think it's better to use the dash. All right. See, the software can easily find the VTS for you. You just need to remove the load and find the actual voltage at the output. Oh yes, here we need to construct the circuit, right? Construct the circuit in figure 2.4. That means we need to, this is circuit 2.4 actually. Here say also say about figure 2.4. So we didn't need to place it again here. Go construct circuit shown 2.4. Also, we need to show the our work here. Okay. Just show our circuit. Our circuit is already here, so we don't need to paste it again under this step. See, doing a double job. Okay, so we come to step 5. Yeah, we need to key in the simulation result. Okay, let's key in the simulation result. Remember the calculated result is the previous step. So this one is I cannot key in, right? This is under the Chrome, Google Chrome. There's no tool for us to key in. We have to use the Edge, Microsoft Edge. Then we key in here. Okay, what's the value? 10.714 and 10.714. Key in this space, and then we cut and copy this. Cut and copy it using another tools. Okay. Transport it into here. All right, then we can start our step 5. So when you come out your own calculated VTH, you have to make sure that you're matching this simulated value. Otherwise, that doesn't make sense. See, if your calculated value is not same with this one, that means most likely you're making a mistake, on your side, not the software side. See, because I'm quite sure this is the correct answer. So if you're getting a different answer, then make sure you double check your step again. Now what? Now we need to find the RTH. Okay. Now let's copy that now. RTH. Remember we have the VTH and RTH, Thevenin V and Thevenin R. These two we need to find out. All right. Let's do the alignment first. Okay. Next, we will calculate RTH. To find RTH, we remove R3 again. So we also remove R3. And then we need to turn off the voltage source by placing a short circuit. Okay, placing a short circuit. And then we try to determine the RTH from the terminal A and B. Something like this. Okay, so we need to copy this figure. We need to copy this figure here. Just copy this figure. 2.5 also. Under the step number 5. Okay, now we come back to our simulation software, our RTSpice. We need to remove this our supply. Just go ahead and remove it. Then we just join the wire from here to here, join the ground. So we need to join the wire to ground because this point is already a ground, right? This point is already a ground. So you just need to join the wire. Let's join the wire first. And then by doing this, can we can we determine the R or not? I don't think so, right? I don't think we can. Just the software is capable of doing that. I don't think the software can allow you to calculate total resistance just by joining the ground here. You see something is missing in the step. Let me double confirm again. Oh yeah, here. We need to wait a minute. Step 5 is calculated. It's not yet simulation. So I'm sure you know how to calculate this R, right? Again, one more time. Step 5 is not simulation. Step 5 is a calculated value. Determine RTH. The way he said determine is mean that you need to calculate RTH, not to use a software to calculate. Okay. That means I need to copy this part. Okay. Let me copy this part. Look at the word calculator. It tells everything. And then the step 6 is actually the. I'm sure you know how to do this by now. I'm going to show you. I'm going to show you here, right here, because it's a part of the tutorials. I consider this as a part of the tutorial. See, we have this one. This component sharing the same node with this component, and this node also sharing the same node. So they are sharing 2 nodes, makes it at least 2 nodes. So that means they are parallel. When they are parallel to each other, that means we can use the formula like this. RTH is equal to the generic formula is like this. This is the generic formula. But the one I prefer is like this. The one I prefer is like R1 times R2 over R1 plus R2 for 2 resistors only. So let's calculate. Okay, let's calculate whether it's correct or not. 10K and 1.2K over 11.2K. Let's see whether this is correct or not. Get the calculator. 10K multiplied by 1.2 divided by 11.2. 1.071. Looks like this number looks very familiar. Let me double check. Yeah, this is the correct answer. This is the correct answer. Not 1.7. Too bad I cannot reverse it. 0.71 K ohm. Okay, since you already know the answer, because I don't want to hide it from you, it's so obvious. Let's key in the result into here. Not into here. Okay, let's key in the result. Save you one more step. Okay. How to get the symbol ohm actually? Okay, you can go to the Google and try your luck here. Ohm symbol here. Copy. Let's see. I can copy here and do here. Yeah, I can do that. Okay. Wait a minute. It disappeared because it cannot show it. It's not so smart to decode the symbol. Let me take away this one, then I think it can show, right? Let me find another symbol. I try one more time. Because I remember this is ASCII code. You should be able to show it. But it won't show it. That means I don't want to force it. Okay. I'm going to use another alternative way. Use a K ohm. I think everyone can read this, right? No issue at all. Just copy this thing, import into our reports. Yeah, we create this empty one. And you need to show the calculation part, right? You cannot just show here because you need to prove how you get it. I will show you answer. Answer is here. Okay, you just need to retype this one into the result section. Show how to do this. First, you need to know what step it is. Step number 5. For step 5, I just quickly type the answer quickly. Okay. I think in the words is powerful enough to recognize this symbol. Yeah, words, but with the background red color. Let me see. I can. Yeah. I have to using a different mode of copy and paste. Wait a minute. Let's do it one more time. Paste only the value, yeah, not the format. It's a capital K or something. Okay. Okay, you need to show every step how you obtain the result, the value like this. Okay, and your key in here, calculated. Now back to the simulation again. Let's look at the step, the simulation step. Okay, let's copy the instruction first. Okay, after this, we have to take a break. I feel a bit tired. Okay, now what we do is we have to use a small trick by placing a 1 volt between the output. Okay, because without the voltage, there's no current flow. It's impossible for the software to give you any meaningful result. So the trick to ask the software to calculate the total resistance here is to by placing one volt, because everything divided by 1 will get a 1. You see? What I mean is something like this, you see. We want to calculate the resistance, right? And this is the Ohm's law. The resistance is equal to V over I. Okay, so if we place a resistance into 1, and then we use the software to determine the I. So the 1 divided by I is our resistance. That means resistance equal to 1 divided by I. So if we can find the I, we just take the 1 divided by I, then we can determine the resistance. Because we use 1 only for the voltage. Of course, you can use 2 here, but people would prefer use 1. You know, 1 is a nice number. So why choose anything other than 1? So to do this, get the voltage component, voltage source from this component, and place it in between here. Okay, then change it to 1 volt. Then we find the current. You see, based on our formula, we need the current. We already press a 1. We find the current, then we can determine the resistance. So this is a trick, okay? This is a trick probably you can use in any other software later on. Okay, let's see whether this works or not. All right, let's run it. We have a current here, but let's convert this. Let's convert this one to current. Okay, let's convert this one to current. How to convert? Right click, delete the dollar sign. The current is for what? For this 1 ohm, right? This time you need to be careful because there are 3 currents here. The one we're interested should be V1, right? As you know, we want to know the current through the V1. Then we use the Ohm's law to divide it to get the R. Okay, so you need to choose IV1, not the IR1, IR2. See? So this is 9. How to read this? 933 microampere. Is this correct or not? Let's try it. 1 divided by 933.33, and let's convert to the scientific. Now 1 divided by 933.33, and then we use the this exp 6 minus. What is a minus? 6 minus. That means the micro, right? Micro. Then you get 1.0714. Exactly the same, right? This is K in K, right? 1.714 K ohm. So by using the trick like this, we can determine the simulation result here. It's not, you will not show directly. You need to go through another step to calculate it. So what I want to do is key in the same result, 1.71, 1.0714. Okay, and simulation result need to show how you get it, but we cannot just keep it type it here, right? We need to copy out. This is only a temporary place only for us to get the result, and then we need to copy this one into our step 6. Save it, and then now is the time to prove how we get it. Also for step 6, simulation. See, the things come back again. Yeah, now it's back to normal. Simulation circuit for step 6. Let's show them the circuit. Just copy and paste will do. Copy and paste it. There's it. The grid line, just leave it like that. See, it's okay. So by doing this, it still doesn't show the actual output, right? Then we need to go through the other step. R is equal to V divided by I, Ohm's law. Therefore, 1 volt divided by 933.33 micro. Now I need to dig out the micro symbol from the words. Yeah, micro ampere. Okay, ampere equal to 1.0714. Okay, let's copy the Ohm's law. copy the ohm symbol. All right, that's it. This is how it's done with the simulation. Here is how it's done with the calculation. Okay, so I presented you two methods how to find the RTH for this simple circuit. Let's see how many steps we have. We have until 10 here, but we need a break right now. You see, getting a bit tired now. I need a break now. We come back later on. We need a quick break. Come back, then hopefully we can get it done by 1 p.m. Okay, let me get some coffee here because my throat is completely dry right now. Okay, let's go for a quick break right now. All right, I'm back now. Okay. Let me see how many steps we have. We have 3 more simulation results. Draw the line. I think it's quite a simple step, right? I think we can quickly get this done. To draw the circuit, simulation results, step number 6. Seven is what? Draw the Thevenin circuit. Just cut and paste this thing. Figure 2.6. Do we need a box like this or not? So I think it's okay. Just draw in the box like this. Since it's a draw, that means we use our hand to draw, right? Okay, let me show the answer. Let me show the answer. The Thevenin circuit is very simple, right? It only has 2 components. One is the no, I cannot draw it here. I have to draw it here. Another. One is the VTH. So line circle plus minus VTH. Thevenin voltage equal to, what is the number? 10.714. Okay, another one is the Thevenin resistance. Okay, RTH, and the value is here. Okay, then the all we have now is the output. The output terminal A and B, and this output can be attached to the external. We put the dotted line. We use a dotted line to represent the external variable. External variable that you can change it. You can change it whatever you want. The external load attached by the user, but this is the original circuit. So this is called the Thevenin circuit, Thevenin equivalent circuit. Then what we need to do is just copy this out and place it under the step 7. So you appear at the next page. It's okay. Then we quickly get this over. Then we can go for tea break, lunch break until 2 p.m. Let's quickly break this over. Say number 8, based on the figure 2.6, calculate IR3. So IR3, remember IR3 is the external load. That means we need to put this on R3 here. It's okay. We use the name RL. It's okay. We can just copy now and see what we can do. Step number 8. Step number 8. You have to be careful. Now the IR3 split into three parts already. You see, like this. So if you just copy it without without double check, you will get the already wrong, you know. So just change this one to the subscript. Based on the figure calculated, looks like the step will only show the step in the result. See. Okay, just put the notes here so that to let people know where to find it. Why I have this kind of error here? Okay. How to find the calculate IR3? So I'm going to leave it to you because it's quite simple, you see. Okay, let me show you some tips. Okay, never mind. Let me show you some tips. I'm afraid that some students may not be so, fully understand what is the purpose of this Thevenin circuit. So let's show the calculation for the state. Calculation for state number 8. RL is actually equal to R3. Is equal to what? What is the original value for R3? We need to scroll the way up to find the R3. It's a 2.3.3K. I purposely put the R3 at 3.3K. I think that the person who designed this one used a 3.3K for R3. Therefore what? He asked us for the current flow to the R3, right? Calculate the IR3. Therefore, IR3 is equal to I equal to V over R, right? V over R. We have only one V. We have only one R. So there were two R's. One V and two R. And these two R looks like they are in series. They are not in parallel. Because you can see they only share one node. The other node, they are not sharing the same thing. The other node they share with the other component. But they're only sharing one node A only. The B is sharing with the power supply. So for this reason, the R is these two resistors are in series. Okay, so you do this and then you can, because you know the answer already, right? The IR3 we already found it just now. I think you know the answer. You know whether you're correct or not. Where is it? Where's IR3? Remember in one step we use a simulator to find the IR3, right? I think it's in the beginning step here, where we simulate the IR3. We place IR3 here and then we simulate it. Okay, but now we down to these two components only. Now we place the 3.3K here and find the current flow through the R3. Okay, R3 is our RL actually, or in this figure is our RL. So you do it yourself, okay? Equal to 2.51. Right, save it. Number 9, last two already. Number 9, construct the circuit in the LT spice inside the RTH and then with the calculate with the R6. Make sure that R3. Now we need to prove whether the Thevenin circuit is correct or not. We need to construct the Thevenin circuit. Actually, the circuit is the same. Or it's already been modified, you see. We need to place back the original circuit, RTH, VTH, RTH, and IR3 only. This is my, let me see whether it's correct or not. Construct the circuit in 2.6. This is 2.6, right? Let's find our 2.6. So we need to construct this circuit and pressing the RL here, 2.3K, and find the current, is it correct or not? So this is really different from the first step, right? The step one is the original resistance. Now we have a Thevenin component and the RL. Okay, just go ahead and do that. Start with the, remove the wire here and remove this, wait, can we copy it and copy it, move and copy or not? Just move, okay? F7, of it here. Remove this, let's cut the wire first, cut the wire. This is going to be our R3, okay? This is going to be our R3. This is going to be our R3, 3.3K. And this is going to be our RTH. This is going to be our RTH. Yeah. 1.0714K. 1.0714K. And this is our RTH. Let's move, let's join the wire first. Wait. Wire. And change the, enter the correct value. Thevenin voltage, 10.714. Okay, now we want to determine the current flow to the R3. It's easy, right? Using the simulator. I'm sure it's using the simulator. Hey, wait a minute. Number 8, right? Let me see. I'm a bit confused. It's step number 8. Yeah, step number 8 already done. Step number 9. Still need to calculate. Or with the calculated value, sorry, with the calculated value. That means we still use the simulation. We're not using a calculated value. Sometimes when you're not reading this correctly, insert the register for R with the calculated value, you see, but we still run the simulator. Okay, measure the current and record them down. So it's a simulated value. And I come back here. Let's click on this one to show the voltage. Okay, you need to run first. Show the show the voltage. Show the voltage at this point, and then we convert this one to the current. And actually, this one is the this one actually is the what? Is the VR3. VR3 here. Okay, so just go ahead and key this right in. Just go ahead and key this right in now. 8.088. Okay, 8.088. Remember, this is a VR3. This is not the VTH. Okay, just double confirm it. Then the IR3, we can convert this one to IR3, right? But we try to show both at the same time. Let's say we click another one. Too bad we cannot move this one. Let's try to move this one, see whether we can do that. Oh yeah, we can. Actually, we can do that. What happened? Okay, let's change to IL3. IL3. Hey, wait a minute, there's no IL3, IL2. Now it's become IL2 already. So this is our, whether we can rotate this thing or not. Let me try to move a bit. Move first. And then rotate. Oh, cannot do it. This is the best we can do already. Voltage and the current. If you want to make it better, probably you can insert some text here. V, according to the question, you say what? Step number 9. VR3, IR3. But this is R2, right? Very confusing, right? But it's okay, actually. Can we change this one to R3 or not? First of all, let's change this to R3. Not to confuse people. Because here say R3, 2.6. But 2.6 it says the RL. But the question say R3. This RTH. This is the RL. RL is our R3 actually. So this is IR3. Just insert another text. This is IR3. Okay, then we just cut and paste this one as a proof. We do it again into the result section. Yeah, this will be the last one already, I think. Let's put for step 9. Okay, for step 9. Simulation circuit for step number 9 is here. And the result, for the result, I think it's better for us to key in into this space here. 2. What's the number again? 451. Worry about the negative sign. We only take the absolute value, absolutely. Then what we need to do is just to copy this up. Let's copy these 2 lines into step number 9. Where is it? Above it. Yeah. But without the instruction, just copy the instruction. Yeah. Hey, wait. Step number 9 is without any value, only the step number 10. Okay. So we need to copy 2 lines here. This is step number 9. Number 9 here. Oh wait. Right form. Then we come to step number 10 is to measure. Actually, the way to measure is to read the current from the software. Okay, done. Measure the current R3. R3 is our RL actually here. I use RL because the theory says here is RL, outload. It's okay if you use R3, I think it's better. I think it's better, but because we already explained to the user RL is equal to R3. We already explained it here. So I think it's okay. Since we already made it very clear, RL is R3. Okay, RL is R3. So it's okay, I think. Whenever you see RL, you just treat it as R3. Then followed by the question. So I will leave the question to you because you have to answer the question to prove that you understand this concept, you understand this topic. So I just copy it under the conclusion. So I will not write conclusion now. because it will be look as almost the same with the previous one. Then I'll just copy it and get it ready when you after you're attending the tutorial 2 and 3, then you can answer this two question. Okay, you can wait. Okay, don't no need to be to hurry to find the answer yet. I change this one to 14 and bold. Okay, you need to write your conclusion here. All right, I hope everything is clear. Now it's time for us to go for lunch. So we will come back about 2 p.m. Actually at exactly 2 p.m. we'll come back. So before I go, I better set this one into a different drive. I'm afraid that later my PC will shut down. Let me, these are all my files, I think, with the document files. So I just need to copy this folder into another permanent place here. Okay. All right, we'll come back for question 3. So now I will stop right here. We'll start the new recording at 2 p.m. So we stop right here.